Hi students, in this video we're going to talk about curvature. All right, so let's draw a curve. We'll use red. So imagine we have a curve that looks like this. So, and let's put a couple of points on that curve. Let's put a point here, and we'll put another point here. And we'll draw a unit tangent vector at point A, and we'll draw another unit tangent vector at point B. All curvature is the rate of change of the tangent vector at a particular point for our parameter. In this case, our parameter is t. The curvature as we get closer to this bend is going to be larger than when we're on the flatter part of the curve. An important distinction is that since both x and y are parameterized in terms of t, that the curvature is the rate of change of the unit tangent vector in relation to the arc length, because we're slowly moving along the arc. So like a small change from like point B, and we'll do like a point C in green perhaps. So what we're really measuring is the rate of change from one point to another. But just like in single variable calculus, you can go from approximating something like a secant line to a tangent line. So if we make these changes very small, we're looking at the instantaneous rate of change at a point. And so again, curvature is the rate of change of the unit vector in relation to where the vector is on the arc. So our rate of change is in relation to arc length. The formula that we have for curvature is we have kappa is equal to the magnitude of the derivative of the unit tangent vector divided by the magnitude or the speed. So that kind of sounds like acceleration, but we can still think of this as just two rates of change. It's the rate of change of the unit tangent vector to the rate of change of position. So the formula is very straightforward. It can get very messy in a hurry if the functions are somewhat complicated. And so in a second video, we'll discuss an alternate version of the curvature formula. All right, so again, our formula is just the magnitude of the derivative of the unit tangent vector and the divided by the speed. So for example one, we have to find the curvature, and we know RT is, all right, so this is a line segment. So we would expect, well, it's not a line segment, it's a line. We would expect a line to have zero curvature. Let's see if that is the result. So what color will we use? We'll use blue. Let's go with blue. So R prime of T is equal to 3, 4, -2, and to do to get our unit tangent vector, we need the magnitude of the derivative. So the magnitude of R prime is the square root of 3 squared plus 4 squared plus -2 squared. So that is 9 plus 16 plus 4. It seems like the square root of 29. So for us, our tangent vector is equal to 3 over square root 29, 4 over square root 29, and -2 over square root 29. And our derivative is t prime of t is going to equal, well, the derivative of a constant is 0, so 0, 0, and 0. And so here our kappa value is equal to the magnitude of t prime, which is going to be 0. We'll actually need that in absolute value. So that's going to be 0 divided by the velocity or the speed. and we get square root 29, which is just 0. So again, we would expect a line to have 0 curvature because it never bends. So that actually makes sense. For our second example, we have a vector in 2 dimensions, and we want to find the curvature formula, not at a particular point. So same process. Our derivative is equal to 1 and 2t. The magnitude of the derivative is the square root of 1 plus, all right, so 2t squared is going to give us 4t squared. And our unit tangent vector t of t is going to equal 1 over, let's write this as a component and get some more room. It's going to give us 1 over, so we're going to write this, all right, so this is the same as 1 plus 4t squared to the 1/2 power. Excuse me. So we'll get 1 divided by 1 plus 4t squared to the 1/2. That's going to be the same as if we just had 1 plus 4t squared to the negative 1/2 power. And then for our second component, it's 2t divided by 1 plus 4t squared to the 1/2. So now you can already see that this is probably going to get messy when we're trying to find the curvature. So the derivative of the unit tangent vector, all right, so for the first thing, we have to do the chain rule. So that's going to give us negative 1/2 times 1 plus 4t squared to the negative 3/2. And then we need to multiply by the derivative of the inside because of the chain rule, so times 8t. So that's all for the first component. And then for the second component, because it is it's a rational function, we're going to have to do the quotient rule. So the derivative is going to be why does it keep switching to the eraser? So it's going to be 1 plus 4t squared to the 1/2 times the derivative of the numerator, which is 2, minus the numerator times the derivative of the denominator, which is going to be 1/2 times 1 plus 4t squared to the negative 1/2 times 8t. And all of that is divided by the denominator square, so really just 1 plus 4t squared. And if we had to simplify this, it's not going to simplify it to anything that's super nice, but it can look a little better. So we're going to get, for the first component, negative 4t divided by 1 plus 4t squared to the 3/2 power. And then for the second component, all right, there's a lot happening for this one. So we'd have 1 plus 4t squared to the 1/2. Oh, that was multiplied by 2. And so then negative 2t times 1/2 times 8 is going to just be negative 8t squared. So minus 8t squared times 1 plus 4t squared to the negative 1/2 power. And all of that is divided by 1 plus 4t squared. So those are our two components. Now we could simplify a little bit farther by, just so we're clear, so that's our derivative of the unit tangent vector. So our curvature is going to be t prime of t divided by, what's the magnitude of t prime of t divided by the magnitude of r prime of t, or the speed. So that's going to be, so in the numerator for this first thing, we would get, actually, let's go back a moment. Let's simplify this second component a little farther. So let's do some side work. Off to the right for this second component, this is the same as 2 times 1 plus 4t squared to the 1/2 minus 8t squared divided by 1 plus 4t squared to the 1/2 power. And so we get a common denominator, and all of this is divided by this 1 plus 4t squared. So we could get a common denominator where we multiply the first term by 1 plus 4t squared to the 1/2. So that would give us 2 times 1 plus 4t squared minus 8t squared. And all of that would be divided by 1 plus 4t squared to the 3/2 power, because then we can multiply this power. The denominator of the numerator times the actual denominator, and that would give us to the 3/2 instead, because what's in the denominator is raised to the first power. And so then if we further simplify that, we would have 2 plus 4t squared minus 8t squared. So this second component actually simplifies to be, is something a little nicer, but still ugly when we have to square it. So we actually get negative 4t over 1 plus 4t squared to the 3/2. And again, if we distribute, the 2 and the 4t squared is going to cancel and make 0 with that. So we just get 2 over 1 plus 4t squared to the 3/2. So now our curvature is equal to the magnitude of each one of those. It's the magnitude of the unit tangent vector divided by the speed. So we already know the speed is 1 plus 4t squared to the 1/2. So our curvature is the square root of negative 4t divided by 1 plus 4t squared. I can write this larger. Goodness. All right. Start over. So our curvature is equal to, in the numerator, we would get the square root of negative 4t divided by 1 plus 4t squared to the 3/2, and that entire thing needs to be squared, plus 2 divided by 1 plus 4t squared to the 3/2, and all of that needs to be squared. So this is the magnitude of the derivative of the unit tangent vector, and we would divide by the magnitude of the derivative, which is we already found this, and that's just 1 plus 4t squared to the 1/2. And so if you simplify this a bit, you would get the square root of 16t squared divided by 1 plus 4t cubed. I'm sorry, 1 plus 4t squared cubed. 1 plus 4t squared cubed. And then plus 4 divided by 1 plus 4t squared cubed. And all of that is divided by the square root of 1 plus 4t squared, or we're going to write it as 1/2. So if you go one step further, we would get the square root of 16t squared plus 4. We could factor 4 out. And all of that is divided by 1 plus 4t squared cubed, and all of that is divided by 1 plus 4t squared to the 1/2. So remember this property, the square root of a divided by b is the square root of a divided by the square root of b. So what we could actually get is the square root of 16t squared plus 4. And so since that's to the 3/2 and we're dividing by 1/2, we would really just get over 1 plus 4t squared squared. All right, so that's a lot of work to get down here. And again, all this would do is tell us at different points of t what the curvature is, the rate of change of the unit tangent vector. So you can see it's a very complicated formula for an extremely simple vector. That's just t and t squared. So again, in our second video, we'll talk about an alternate version of this for when the problems get very complicated. Like algebraically, this worked out pretty nicely because we could condense a lot of stuff, but it could get messy in a hurry. Example 3, you have to find the curvature of any circle. So we're talking about a circle, and we have to use t as the parameter. Any circle, we're just gonna make we can't. All right, so don't use a lowercase r because we already have a lowercase r. So we'll use capital R to be the radius of the circle. So r equals the radius of the circle. So then the x component is r cosine t, and the y component is r sine t. So our derivative is equal to negative r sine t and r cosine t, and the magnitude of this vector is let's see, it's the square root of r squared sine squared t plus r squared cosine squared t, which we already know sine squared plus cosine squared is 1. So when we factor out the r squared, we'll have r squared times 1, and the square root of r squared is r. So our unit tangent vector is equal to negative sine t cosine t, and that's because we just would have negative r sine t, we divide that component by r, and we'll have r cosine t, and we divide that component by r to get our unit tangent vector. So then the derivative of the unit tangent vector is negative cosine t and negative sine t. And so then the curvature at any point is going to be the magnitude of the unit tangent vector's derivative. So the magnitude of t prime of t, which we can clearly see is going to be cosine squared plus sine squared, which is going to equal 1. And we divide that by the speed, which is r. So our curvature for any circle is 1 over r. So for a circle of radius 2, the curvature is 1/2. For a circle of radius 4, the curvature is 1/4. For a circle of radius 100, the curvature is 1 over 100. And it makes sense that as the circle gets larger, the rate of change of unit tangent vector should get smaller, because you're making the circle flatter and flatter as you make it larger. So like a circle of this size is going to have a lot of curvature because you have to bend a lot as you move around it. So if we put like a unit vector here and another unit vector here, even though the curvature is constant, it's sharper because the circle is smaller. So if we had a bigger circle, we'll say like one that's this size, then we can see that the curvature at any point, again, though constant, is not as sharp as the curvature here. So that's it. So again, the curvature of any circle is 1 divided by the radius of the circle. And for our last example, we're going to find the curvature for cosine squared t, sine squared t. So our derivative is 2 cosine t times negative sine t and 2 sine t cosine t. The magnitude. All right, so just so we're clear, this is negative 2 sine theta. So 2 sine t cosine t is equal to sine 2 theta. That identity might come in handy in a moment. We'll see. So r prime of t, the magnitude is 4 cosine squared t sine squared t plus 4 sine squared t cosine squared t. So together it's the same thing really. So we get 8 cosine squared t sine squared t under the square root, which is just going to be cosine t sine t times the square root of 8. So you could say, let's just leave it as the square root of 8, even though the square root of 8 is 2 square root 2. I would just leave it as the square root of 8. So our unit tangent vector is, let's actually write this out. So 2, we'll say negative 2 sine t cosine t and 2 sine t cosine t, and all divided by square root 8. Actually, you know what? Let's make that 2 square root 2. It's going to be useful. So we'll make that 2 square root 2 sine t cosine t. So we're dividing the vector by the speed. So as a component, we're going to just get negative 1 over root 2 for the first component because the sine and cosine cancel. And for the second component, we get 1 over root 2 as a unit tangent vector. So anytime the unit tangent vector is constant, the curvature is going to be 0. So immediately we would see that t prime of t is equal to 0. And so the curvature is going to be 0 divided by 2 root 2 cosine t sine t. So that doesn't actually matter when the numerator is 0. All right, so that is curvature using derivatives. There's a way that we can do this using cross products and some powers of the velocity vector. We'll do that in the second video.